your tutor for OFP 016 Chemistry for Foundation Program. And today we are going to cover our second knowledge area, that is atomic structure and periodic table. In this knowledge area there are two modules. Module 3, which is on atomic structure, and Module 4, the periodic table of elements. You will recall that in the first knowledge area of this course, we defined an atom and we discussed the atomic theory, including its modification that resulted into the modern atomic theory. Therefore, in this part, we will discuss the structure of atom, mainly referring to the arrangement and relationship among the subatomic particles in the atom, and we will also describe the periodic table of elements, including how to write electron configuration of elements, quantum numbers, arrangement of elements in rows and columns, distinction between elements, different types of elements, and also we will see the periodic variation in physical and chemical properties of elements. Some of these concepts will be just a revision from your lower level of education, and some of them may be new to you. Now, after studying this lecture, you are supposed to be able to describe the structure of an atom. You will be able to describe the relationship between the different subatomic particles and their arrangement in an atom. Also, you can describe the 4 quantum numbers and describe the atomic spectra. Also, you are supposed to be able to write electronic configuration of atoms and ions and define the periodic table of elements, including describing the arrangement of elements in periods and groups, as well as the variation chemical and physical properties among these elements. Now let us recall the definition of atom. We say that an atom is the smallest particle of an element which can take place in a chemical reaction. It may or may not be capable of independent existence. So the origin of this idea of an atom. First of all, the word atom comes from a Greek word, atomos, which means indivisible. So it was said that an atom is the smallest particle that was not be able to be divided. Although the early scientists believed that the atoms were indivisible, as we saw previously in our first lecture, in the Dalton's atomic theory, and that it was the smallest and the most fundamental unit of matter, the concept was continued to be researched by various eminent scientists such as Goldstein, Rutherford, and others in the first part of the second part of the 19th century, and also the later part of the 20th century. So in the course of this research, it was established beyond doubt that atoms were not the smallest particles. There are other smaller particles that are called subatomic particles, which are electrons, protons, and neutrons. So the atomic structure was first studied by the scientist by the name of Ernest Rutherford and his colleagues, and they established the Rutherford atomic model. In this model, the structure of atom is described to consist of positively and negatively charged particles, and also the neutral particles, that are neutrons, revolving around an orbit in varying distance from the nucleus. So the constitution of the nucleus and the arrangement of the electrons differ within various chemical elements. That is according to the Rutherford atomic model. So we can perceive the image of an atom like one having a central nucleus in which there are number of protons and neutrons, and there are orbits around it in which the electrons are revolving. That is the structure of an atom. The structure of an atom was first described by a scientist by the name of Ernest Rutherford and his colleagues, and they described this structure as consisting of a nucleus with positively charged particles and neutral particles surrounded by negatively charged particles known as electrons that are revolving in orbits at varying distance from the nucleus. So constitution of the nucleus and the arrangement of the electrons differ from one element to another. And therefore we can perceive the image of an atom as that one of having a central nucleus with protons and neutrons surrounded by new electrons that are revolving in orbits. So an atom is composed of subatomic particles, which are electrons, protons, and neutrons. Electrons are very small, negatively charged particles that are indeed a fundamental part of an atom, whereas protons are positively charged particles that can exist freely in an atomic nucleus. And the neutrons are almost identical in mass to the protons, but they do not carry any charge. These are neutral. And the number of protons is almost equal to the number of electrons, making an atom to be neutral. That is, it has no charge. So the atomic number is the number of protons in the nucleus of an atom, which is actually the identity of an element. So we have seen that the relationship between the subatomic particles now is such as the positively charged particles, which are protons, balance the negatively charged particles, which are electrons, and thus the atom is held together by the electromagnetic forces. Because neutrons have no electric charge, they add to the strong force of attraction. And this is compared to the solar system, whereby we have the sun at the center and the planets revolving around the sun. That is a comparison of the atomics, structure of the atom. Now, since the number of protons is equal to number of electrons, the atom as a whole is electrically neutral. Now, all protons, regardless of from which element, and all neutrons, they are just the same. And all electrons are also exactly the same. Now, what differentiates one atom from another, or an atom of one element to an atom of another element, is the number of subatomic particles in each element. So the mass number, as we said, is the total number of protons and neutrons, which is the identity of an atom. Now, this model had some drawbacks, has some limitations. For example, the model proposed that electrons revolve in high speed in circular orbits around the positively charged nucleus. However, the result of this would be that an atom would not be stable. Why? Because in the course of revolving, there would be some energy discharge, and eventually they may have some acceleration and they may fall into the nucleus. But that does not happen. And why? So the Rutherford model could not explain the stability of an atom. Another thing is that the model proposed that electrons revolve around the nucleus in fixed orbits. However, it could not specify the orbits and the number of electrons in each of these orbits. So that was another drawback. Also, it was observed that the elements give some characteristic line spectra. But this line spectra also could not be explained. Now, after the discovery of the fact that an atom is made up of these small subatomic particles, scientists were looking for some answers. Especially now there were some drawbacks from the Rutherford model. For example, now the first question was, how now can we account for the stability of an atom? And also, why are both physical and chemical properties of one element different from the other? And why do different atoms combine to form molecules? Those are some of the questions. And what is the origin and nature of the electromagnetic radiation that is emitted or absorbed by atoms? Those were the questions. Now, following these questions and further research, there was another scientist, a Danish scientist by the name of Niels Bohr, who suggested another model by studying the behavior of electrons in the hydrogen atom. Now, this scientist based his research on the existing Rutherford model and used the Planck's quantum theory. Now you can recall some of the postulates of the quantum theory. One of them is that atoms can exist in each and in certain states characterized by different definite amounts of energy. And when an atom changes its state, it absorbs or it can emit an amount of energy. And this energy is called electromagnetic radiation, which is just sufficient to bring that electron into another state. And another postulate of this theory was that when atoms absorb or emit light in moving from one energy level to another, the wavelength of the light is related to energies in the two states given by that specific equation. And now, it also followed that energy state of an atom can be described by a set of quantum numbers. And these are like addresses of an atom. And quantum numbers are associated with individual elements or electrons in an atom. That was basically some of the postulates of the quantum theory. Now, this new model, which was the Bohr's model of an atom, was put forward, modifying the previous model by Rutherford, addressing some of the problems and limitations, and describe the structure of an atom now by incorporating the electromagnetic wave theory. And this new model now accounts for the series of discrete wavelengths in the emission spectrum of hydrogen. And it agrees that the atom really consists of small, dense nucleus surrounded by orbiting electrons. Comparing it was similar to the structure of the solar system. Now, the attraction, we know that the attraction in the solar system is given by the gravitational force. But in this case, the attraction is provided by electrostatic forces. So, electrons can jump from one orbit to another by emitting or absorbing energy. And in the movement of electrons between these energy levels, the electrons now produce this spectrum. And now this model established a set of numbers called quantum numbers, which we say that they are like addresses. We know that the address may have a street number, may have a regional number, and so on and so forth. So the electron is described by these four specific quantum numbers. The first one is the principal quantum number, the azimuthal quantum number, magnetic quantum number, and the spin quantum number. Now, this is pretty much a different kind of atomic model that was put forward by Bohr. You can note now that there are very specific orbits for electrons to revolve in. And this was the model for nitrogen atom as an example. Now, what were the usefulness of this new model? It's that it explained the stability of an atom, which was not done by the previous model. Now it was discovered that electrons cannot lose energy as long as they stay in their particular orbit. Another thing is that this new model explains the line spectrum, using the example of line spectrum of hydrogen. When an atom is subjected to electric discharge or high temperature, it may jump from the ground state to an excited state. And during this jump, energy is emitted in the form of photon or light of a definite wavelength. Now, to answer the other question, why do different atoms combine to form molecules, which the scientists were trying to research on? It was discovered that atoms form chemical bonds with one another when there is an electrostatic attraction between them. And this attraction is based on the properties and characteristics of the atom's outermost electrons, which are also known as the valence electrons. And atoms form chemical bonds in different ways. They form chemical bonds common known as covalent bonds, metallic bonds, and ionic bonds, which we'll discuss in our future lectures. Now let's discuss a little bit on the electronic or electron configuration. What is electron configuration? This is the arrangement or distribution of electrons among the various orbitals in the principal subshell by following some specific rules or guidelines. And usually the arrangement or the filling of the electrons is starting from the lowest energy, which is known as the ground state. And the order of filling these orbitals has been established by doing some experiments. Now, what are the rules that are guiding this arrangement of electrons in the shells or in the orbits? The first one is we have the Aufbau principle. This one says that electrons occupy orbitals in a way that minimizes the energy of an atom. That is, they start to fill the lowest energy orbital available. And the second guideline for filling electrons in the subshells is the Pauli exclusions principle. In this case, it is stated that no two electrons in an atom may have all of the four quantum numbers alike. And the last one is the Hertz law, that an atom tends to have as many unpaired electrons as possible. That is, pairing of electrons will only start when each of the subshells has been singly occupied. Now, in this case, we can note that the order in which the filling of orbitals will be in such a way that you start with the 1s and so on and so forth, as shown by this diagram. Now let us see examples of electron configuration or electronic configuration of some of the atoms. For example, we have hydrogen atom, which has only one atomic number, and that is it has only one electron in the valence shell. And you can see the second one is helium with two electrons. And you see that the electron configuration follows the three principles that we mentioned earlier. So that is an example. We have up to nitrogen with 11 electrons. These are just some examples of how the electrons are filled in the subshells. Now, how can we write electron configuration? There are two ways. The second way, the one we showed in the previous slide, is the first way. And we have another way of writing the electron configuration, which is known as the core valence notation. We know that the valence shell is the outermost shell of an atom, and that if the valence shell is removed, what remains is called the core. And the core now resembles the inert gases configuration that are chemically inert. So we can simplify writing of the electron configuration by using the inert gas configuration and followed by the valence shell configuration. For example, we simply write the valence shell that correspond to that particular element. For example, for oxygen, which has atomic number 8 and which has 8 electrons, so it has 2 electrons and 6 electrons. But we know that the 2 electrons are corresponding to helium. So instead of writing the full configuration, you just write helium in closed or box brackets, followed by the valence shell configuration, in short. Likewise for chlorine, which has 17, so it corresponds to neon, followed by the outermost shell configuration. Now, let us see how we can write the configuration of ions. This was the configuration for atoms. But what are ions? We know that most atoms do not have 8 electrons in their valence shells. That is only for the noble gases. Now, some atoms, in trying to achieve the inert gas configuration or the octet shell, they will have to gain a few electrons or they will have to lose a few electrons. So atoms which have 3 or fewer valence electrons, they may have to lose those few electrons so as to gain the octet shell configuration. For example, we have sodium. And sodium has, we know it has 11 electrons. So it will have 10 electrons and then 1 electron in the valence shell. So it is easier to lose that electron in the valence shell so that it can achieve the octet shell. And in doing so, now the sodium atom becomes an ion with a positive charge. Likewise, for atoms that have nearly 8 electrons, for example, they have 6, 7 electrons in their outermost shell. Instead of losing all those 6 or 7 electrons, they will have to gain only 1 electron so that they have the octet shell. So for example, chlorine, which has 17, it has 17 electrons. So there are 7 electrons in the outermost shell, with 10 in the other shells. So for chlorine to achieve the inert gas configuration, it will have only to gain 1 electron. And in doing so, the chlorine or atom now will become chlorine ion with a negative charge. Now, what is an ion? We have already defined it. It's therefore an atom that has gained or it has lost 1 or more of its valence electrons, giving it either net positive or net negative charge. So there are 2 types of ions, cations and anions. So with positive charge, they are called cations. For example, now sodium, which has a positive charge. And anions are those with negative charge. For example, chlorine, after gaining 1 electron. Now, writing the electron configuration of these ions is just the same as writing the electron configuration of their respective atoms, except only that now it has just added a few or subtracted a few of its elements, electrons in the outermost shell. For writing the electron configuration of an ion, you just have to first write the electron configuration of the atom, and then you remove or you add the electrons that have been gained or that have been lost. As simple as that. Now let us move to our second part, which is periodic table of elements. And we know that establishment of the periodic table of elements within the effort to classify elements. We know that elements are the basic units of matter, as we discussed in our previous lecture. Now, by 1800, there were only like 31 known elements. But currently, there are about 118 known elements. Some of them, they are natural, and most of them, they are natural, and a few of them, they are synthetic. That they are made by man. Now, these electrons, we know they make billions maybe, of compounds. Now, each element differs from others, and yet there are certain similarities among the elements. So it was seen that it was necessary to classify these elements based on their similarities and differences. And as we mentioned previously, that atomic number is the most fundamental property of an element. Why? Because no two elements have the same atomic number. Now, the description of, or the arrangement of these elements in the periodic table of elements was based on their atomic weights. Now, there were several attempts. We cannot go into details on the history of it, but the most successful one was the Mendeleev periodic table, which was published around 1872. Although it also had some drawbacks which were improved later on with some discoveries done, but the table was continued to be modified. For example, there were discovery of the noble gases in the 1900s, which were not there when the Mendeleev table was published. So actually we can generally define or explain periodic table of elements as a tabular arrangement of all the known elements ordered by their atomic numbers. And we know that the atomic number refers to the number of protons and also by their electron configurations. Now that is an example of the modern periodic table of elements. You can note that there are seven rows and 18 columns, and the rows are known as periods, and the columns are known as the groups. The vertical ones, they are known as the groups, and the horizontal ones, the rows, are known as the period. So in the modern periodic table, we have the modern periodic row that basically played a significant role in the establishment of this modern periodic table of elements. We are told that the physical and chemical properties of elements are a periodic function of their atomic numbers. That is, if elements are arranged in order of increasing their atomic numbers, the elements with similar properties will be repeated in certain regular intervals. Now, with gradual increase of atomic number, there also occur a repetition of similar valence shell configuration or the outer electron configuration. And elements in the periodic table are organized in a manner that is used to show recurring chemical as well as physical differences, trends, similarities, and so on and so forth. Now, we mentioned earlier when we were discussing the classification of matter that elements can be classified as metals, non-metals, and metalloids. You will recall that in our first lecture. Now, pure elements are rarely found in nature. Elements are usually not found very pure, 100% pure in nature. But to say that the only two elements that are found pure in nature are gold and platinum. Maybe they have discovered more, but there were only two that were found pure in nature, which is gold and platinum. And metals are usually solid at room temperature. That is the property of metal. They are good conductors of heat and electricity, and they are ductile and malleable. While non-metals have quite the opposite properties of those of metals. And metalloids, they have properties in between those of metals and non-metals. For example, silicon is one of the metalloids. Now, for simplification, elements are arranged in groups, as we say, but these groups have been given special names. For example, group 1A are known as alkali metals. You may already know this from your previous knowledge of chemistry. And elements in group 2 are known as alkaline earth metals, while group 7 is halogens, and group 8 are rare gases or noble gases. Now, why are elements in these groups having the same properties? We noted that all elements in each group have similar electron configuration, and that now plays a very important role in on the type of bonds those elements will form, whether it is covalent bond or ionic bond, metallic bond, and so on and so forth. This only depends on the outermost shell configuration of the particular element. Now, for example, let us take an example of elements in group 1, which are alkali metals. Let us take the example of the first 6 of them: lithium, sodium, potassium, rubidium, cesium, and francium. You find that they all end up with S1. Look at the outermost shell of each one of them. You find that it is 2S1, 3S1, 4S1, 5S1, 6, up to 7S1. So we note that the electron configuration of alkali metals in N is NS1. It is because of this similarity in electron configuration that elements in groups have similar properties. Now, for example, we have the noble gases: helium, neon, argon, krypton, xenon, and radon. They are a family of gases that are known as noble gases, and they have octet shell, that they have 8 electrons in their outermost shell. Their outermost shell is completely filled, and that's why they are noble and they do not make reactions easily. Another example is the halogens, and this is they have 7 electrons in their valence shells. It's just 1 electron short from achieving the octet shell, and so that they gain 1 electron to achieve the octet shell. So these are among the most reactive elements, especially fluorine and chlorine, because of that nature. Another group is the alkali metals, which have single valence electrons, and this electron can easily be lost, and these elements are also extremely reactive. And we have another group of alkaline earths which have 2 charged ions, and they have low solubility, and so on and so forth. So properties of elements are basically described in this nature of their group properties. We noted that there are 7 periods from the top of the periodic table to the bottom, that is numbered 1 to 7. Now we noted also that the period number corresponds to the highest principal quantum number from that example of the group 1. Note this, group 1, you see that there are 7 rows, and we noted that among the 7 periods, each element, outermost configuration, corresponds to the highest principal quantum number. For example, 1 for hydrogen, 2 for lithium, 3 for sodium, 4 for potassium, and so on and so forth. And we also noted that in this modern periodic table there are 18 rows. Now this brings us to the end of our lecture. In this lecture, we discussed the structure of an atom, including the arrangement and relationship of the subatomic particles, that is the protons, neutrons, and electrons. We have also discussed the Rutherford model, and we have seen some of its drawbacks, which were later modified, and we came up with the Bose atomic model. We also discussed how electrons are filled in different subshells of an atom using the 3 guiding rules. That was the Aufbau principle, the Pauli exclusion principle, and the Hertz rule. And also, we noted that electron configuration is the distribution of electrons in various orbitals of an atom, and that there is a direct relationship between electron configuration of an atom and its position in the periodic table. We also discussed that atomic number is the most fundamental property of an element, which is actually the identity of an element. And we define the periodic table of elements as a tabular arrangement of all the known elements ordered by the atomic numbers and electron configurations. And that arrangement of elements in groups and periods are directly related to the chemical and physical properties of that particular group or period. And that elements in the same group show marked similarities. And why? It is because of the similar atom shell configuration. So this knowledge, these concepts will help you very much to understand further concepts that you will learn in your future courses in chemistry. Thank you very much.